Hello, everyone. I think we can start with the webinar. Welcome to all of you to the new series of to the new episode of the series of webinar that we have organized at Frenetic. My name is Martina, and I'm responsible for marketing and communication at Frenetic. Today's webinar is called How to Design an Inductor, and it's based on the article that our CEO, Dr. Molina, wrote a couple of weeks ago and published on his newsletter and on his blog. This seminar forms part of a series that we have decided to organize at Frenetic since last month. So we will organize a monthly webinar. And of course, our idea is to cover very different topics within the power electronic world. We would like you to participate actively to these webinars, let's say, and please feel free to send us your ideas and your proposals on the topics that you would like us to cover. We are very open to any kind of topic, of course, within the power electronics world. Feel free again to send us your proposals. You can contact us through our website, frenetic.ai, or through our LinkedIn page, where you can find us just looking for the name of our company, of course, Frenetic. You can also contact us by replying to our weekly newsletters that is sent every Monday. And of course, if you're not registered, please feel free to register now. Before starting with the seminar, we would like to apologize with our friends in Brazil and Switzerland. We didn't do it on purpose. We didn't know that you were playing the football match today. Of course, we hope you chose to follow us instead of watching the game. But still, if you're missing this, don't worry. This seminar will be available in a recorded video in the next days. I would love to be watching the football match, the football World Cup as well, but unfortunately, Italy decided not to qualify for the second time in a row. So here I am with you today at the webinar. Jokes aside, here are connected our two speakers of the day, Chema Molina and Nicieza. Please, you can start.
Thank you, Martina. I think that there is still a lot of people connecting. Then I will to start sharing my screen while the people arrive and explaining a little bit about how we are going to proceed. Well, thanks, Paul, for attending this webinar. I know that, as Martina said, a lot of people will be playing, well, watching the game of football between Brazil and Switzerland. Good luck to both. As you can see, in Spain, we have a great team now competing, really showing a very good performance. And well, watching the attendees of this webinar, looks like there are fewer women in this webinar than in the stadium of Qatar. We had to do something to attract more people to this kind of webinar from just not well, jokes aside. First, I would like to start explaining how this webinar will work. The first value at Frenetic is honesty. Then I would like to explain why we decided to create these webinars. At the beginning, I thought to write some guides for designing magnetics for new engineers or even for our own purpose, internal purpose at the company. But at some point, we realized that if we were praying about honesty and trying to create a great community of power electronic engineers, why we are going to keep just for us all this knowledge. And also, I have to be honest again, is that if you force yourself to try to explain something to someone, then you have to understand much better what you are going to explain. You review the basics, and it's a very nice experience to study something that in theory you already know, but you learn a lot of new details. And very important thing is that this is not a commercial webinar. Therefore, in case that we use in some calculation, Frenetic Online is just to accelerate some procedure, but all the calculations and everything we are doing here can be done using the equations, the basic equations we have in the articles we have shared. I think that all of you have seen, but if not, in the email after this webinar, we will send you the links for the articles. There are two articles. One is how to design an inductor, and the second one is how to design a 12.5 kilowatt boost inductor. And in those articles, I really invite you to open the article also to, if you have two screens, to follow the conversation. Because in the slides we will use, we haven't put it all the details. It's not possible. Then it's interesting for you to follow with the article. And the reason I told you is not a commercial webinar is because we won't answer questions about Frenetic Online, because this is not a commercial event. If you want to know something about Frenetic Online, you just can schedule a call with one of our field application engineers or someone from our sales team. But today we are going to answer questions about how to design inductors. We don't know everything, then probably some point there would be questions that we have no answer, or someone even in the audience has more details than we have. That could be good, because then we will learn something new, and everyone will learn, and that would be great. But as I said, in the questions, we will only answer questions about how to design magnetics. The structure of the webinar is going to be very simple. We have some slides to review the basics that we describe it in the articles, and that ends with two examples of two inductors, two DC, high frequency DC inductors. Then we will explain the basics, and then at the end of that, we will use some calculation. In that case, we will use Frenetic Online just for doing the calculations. It's not just, as I say, as a let's say commercial part, because we will use just that for explaining the calculations and the comparisons. That means that we will use, for example, the equation for the magnetic field is something that you can do just by yourself, and the data of a standard course of material that is public, and you can go to the websites of the manufacturers that we will use during the webinar, especially ferrocube and magnetics. And I think that that's all. Everyone is already ready here. Then let's start. Well, the first thing I'm going to explain is the table we are building about inductors. In this table we are building here, the classification, as always in my mind, is relatively with the waveforms of the components we are talking about. Then in inductors, if we check which is the type of waveform that these inductors can be working with, we have mainly two different types of waveform, DC and AC, and a combination of DC and AC currents. Then in the first block, we have, let me see if I can use, okay. Then in the first block here, we have the DC currents. In DC currents, we classify between low frequency and high frequency. Since we work only mainly in high frequency, when I'm talking about low frequency, I'm still talking about kilohertz, okay? I'm not talking about very low frequency, about a few hertz. And here, what we can see is that even for low frequency or high frequency, the most common, the common materials that we will use are powder or ferrite. And the main applications of these are back, boost, or just the output filters of different converters, like a full bridge, for example, or any other. Second, we have the inductors that are suffering easy currents. And in DC currents, we have two, again, low frequency and high frequency. Here, I'm talking the low frequency can be in the lower values of hertz, because mainly this is for application like EMI, for reducing the noise. Then here we are talking about pure AC waveforms. And here we can use electrical steel, powder material, amorphous, or nanocrystalline. As I say, main application is differential mode filters for EMI. Common mode filters I won't consider here. That would be another category because it's kind of a couple, but mainly differential mode. If we move to the high frequency cases, then what we are talking about here is inductors that are in series with a transformer, mainly resonant converters like LLC, or even just a full bridge with a series inductor, because this is also a AC current without DC bias. Always I'm talking here about without DC bias. If you will have a DC bias, then you will be talking about a DC inductor, even if the DC bias is very low and the ripple is very high. But here we are talking about zero DC bias. The current is pure AC. And here the main materials again are very similar to in the DC case is ferrite and powder materials. Finally, I have included the PFC because it's the next ones we will write an article about how to design. That is PFC. I have just the qualification for different type of control modes or modulation for the PFC, CCM or CRM, but at the end is the same from the perspective of the material, powder, ferrite, or amorphous. And the application again is PFC, is the most common one. Okay, now that we have cleared the table, we are going to explain the different design methods. Probably there could be more design methods, but this is the ones that we have studied, and at least I have even tested by myself. And even our design method for magnetics, not just for inductors. And we will see in which cases it's better to use ones or another. In the article, you can write, let's say, more details about the area product method, especially because there are more equations. But let me explain some basics about the area product. The area product method basically consists on calculating a value that is called the area product of your converter. In this calculation, basically, there are some inputs that are the output power of your converter, the increment of flux density that you will like to have in your or you will have in your transformer, the switching frequency, and then some factors that are depending of the topology. Then once you calculate this value using the equation that is in the article, then you have a value that is whatever, 2, 1, 3, doesn't matter. Then you go to the table of standard cores. And in this table, each core has a specific value. And here is where you can see the equation that depends of that is a multiplication of the area of the window. That basically means how much copper can you put there. The space you have to put windings, multiplied by the area of, the effective area of the core. That means how much magnetic floods you can put or you can try to get before saturating or before having very high losses. And in this relation, once you have the value from your power converter, you go to the table and then you choose one that is a little bit greater than the value that you from your converter, and this component, this core will be the selected one, and then you can design the converter. I mean, you can design the magnetic starting from this core. And this method is very well described in the literature. Actually, I think that there are some softwares or applications that they use it, and it's not very optimal because there are a lot of assumptions, but especially for transformers, it could work. And especially for forward or flybacks, I mean, the calculation could work. It's not rocket science. The next method could be very simple at the beginning, that is called maximum losses. It's the first method I read in my life. It was in the Indctor books, and basically consists on defining, I mean, doing the design in the reverse way. You define which are the maximum losses you want to have in your component, and then you would start doing the calculations in the reverse way. Even in the Indctor book, they define the maximum temperature at the beginning. It's like the maximum delta temperature they want to have, and then they go in that direction. But if we focus here in the basic maximum losses case, with the typical application, let's say that you have a 100 watts power converter, and then you want to, it's a back converter, 100 watts, you want to apply this method, and you know that you want to have around 90% of efficiency, then you say, okay, that means that I will have a total losses of 10 watts. Then you take those 10 watts and you split those losses between the components. Usually, I recommend, as a rule of thumb, going between 1/5 and 1/6 of the losses to the magnetic. Then that would mean, okay, this, of these 10 watts, 2 watts will be the losses of magnetic of my inductor. Then of these 2 watts, then I can split the losses between the core and the winding, or I mean, in different proportions. For inductors, depends a little bit about how the magnetic flux is and the kind of the type of magnetic, but usually you can have more losses in the winding in some cases. But for example, in transformers, you can split half and half. I mean, that could be a good design of a transformer, that the losses are 50% in the core and 50% in the windings. And this is the maximum losses method. And well, as a recommendation, this method is very useful for transformers, as I said, because the split of the losses are 50%, and it's a good recommendation, and it's something that used to work. And finally, the energy method. For me, the energy method is the most useful for inductors, because as a rule of thumb, they say that the energy stored in at the end an inductor, most of the cases is storing the energy in the operation of the converter. Then what you are defining with this equation here is the energy that you want, or not you want, is that the energy that need to be stored in the component during the operation of the converter. Then let's say you have a 100 watt back inductor and back converter, then you have a value of the inductance and a value of current that is going to go through the inductor. Then you are able to calculate the energy that is not going to be stored. And the people used to say that the energy is stored in the gap. Then when you are going to do the calculations, basically you have to find a combination of gap and the core and the number of turns to have this energy stored. And this is a good game for doing an optimization of an inductor, because if you don't take in consideration that, you can have a very high value of gap, and then you will have a lot of losses due to the proximity and the skin effect. Fringing flux. The fringing flux you will have due to the gap, and then at the end there are a lot of additional losses that you are not considering from the beginning. Then this is something we will see in the sample. But this is the method that I would recommend for using for inductor design. But as I said, I mean, you can use the others, and for sure you will get a good solution if you apply the good rules. Then if we go for a particular example with this this method, let's take, for example, a buck converter where we will have an inductor, and it's a 48 to 12 volt buck converter. This voltage is very typical also in automotive industry. Then we have is a 120 watts, and we have some limitations. Then the first thing we have to do for doing the design of the inductor is to extract the information from the waveform and from the specifications that are needed for doing the calculations. Then if we run the simulation, just of the simulation or just with basic equation of the buck converter, you can find that, well, the most important value, one of the most important is inductance, okay, 22 microhenries for this case. The DC value of the current, DC value, that is basically the bias, the DC value. The ripple, in this case, I have wrote the peak of the ripple, that is 2.24. That means that the ripple will be 2 times this one. The add of the DC plus the peak AC, you have the total peak of the current. This blue line is the current, then the peak here is going to be 12.24, and the switching frequency. Then with these elements, we are able to go to the energy method. Of course, we have some limitation for the mechanical. We have 25 millimeters. That is something we will consider during the process. As I said in the article, the limitations about isolation in this case are not going to be described in detail, because at the end it's an inductor. There are only one winding, and for these values, using just the classic, I mean, the selection of the material, the proper material for the windings will be enough. But of course, if we will do a professional end component, we will have to review these standards to be sure that we are complying with the creepage, clearance, and the isolation. Okay. Then don't consider that this is just all the security that we have to check. Okay, then now I have the information about the inductance, the current, I mean the waveforms, and the power of the component of the converter, and I go to the table to choose the material. If I check for the DC high frequency case, I have 2 options, ferrite and powder material. And then I'm going to call my friend Lucas, that he is going to give us some light. I mean, now, why will we choose ferrite or powder material in this case? Lucas?
Hi, Chema. So in this case, we can choose both, actually. We can either go for a powder or for a ferrite. But I have to say that when we have a relatively low inductance, below 30 micro, 40 micro, and a relatively low amount of current, below 20 amperes, even 30 amperes, the performance in both is going to be kind of similar, but the ferrite is going to be cheaper, because ferrite is cheaper than powder. Therefore, we can go for a ferrite in this case. Yeah.
Okay. Then let's choose ferrite. Sorry.
Yeah, and then when it comes to materials, this is a little bit, here we need more explanation. So in ferrite materials, we normally have three different types of materials. Ones that are for very high frequency, like in the case of ferrous tube, these are the 3F36 and 3F46. And yeah, these are mainly used at these high frequencies. Then we have these materials where we have a flat core loss curve. So this means that for a wide range of temperatures, the core losses are relatively flat. These are the 3C95 and 3C97. And then we have materials that are optimized for a very specific temperature, like for instance, 3C96 or 3C98, which are optimized for 8 degrees temperature. And then we have the materials that have a larger magnetic field saturation, which is the 3C92. And what is the magnetic field? At the end, the magnetic field is the product of the inductance by the peak current divided by the number of turns and the cross section of the core. So if we have a material able to withstand more magnetic field, this means that we can either choose a core with smaller area or with less number of turns, which will mean lower losses in the windings. So for DC inductors with ferrite, we are mainly interested in this material with ferrite that has a high magnetic field saturation value, which in this case is the 3C92.
Okay. Then, as Lucas said, well, we have choose ferrite material for this case, and when you go to the tables of ferrite materials, we have choose ferrous cube because well, we have all the data. I mean, all the raw data from the measurements, the very different measurements, and allow us to have very accurate calculations. But at the end, these tables are very similar for other manufacturers if you want to check other manufacturers. And what is important is to being able to classify the most, well, why choose one material or another. In this case, for example, that we are going to 3C92 due to the maximum field capacity and the frequency. But it's important that you always talk with especially for materials, because it's not a straightforward decision just checking the dataset and selecting one material. I mean, there are a lot of parameters that need to be considered, and this is a recommendation that nobody told me. And when I made the first inductor, I go to the manufacturer and I realized that I was choosing the grown material. And I think that one of the main work of the materials manufacturers is to correct the material that you are choosing when you are designing a component, because you are choosing the raw material for that application. Then this is interesting to learn. Okay, then here at the end is the 3C92. And then we have chosen 3 different cores and 4 different gaps to calculate which is going to be the most, well, the best one for this case. The value of mean here is calculated. I mean, in the article is the equation, but basically is the 0.5 multiplied by the inductance multiplied by the current. And then with this energy, this is the minimum energy we will have to store. Then we calculate the energy that can be stored in this particular course for this particular material, 3C92, for these gap values. Lucas, could you explain us why those values of gap are not others, and why these 3 cores and not others, while we know that there are hundreds of solutions in the market?
Yeah. Well, first thing is we have a height limitation of 25 mm, so that automatically defines, or let's say, give us an idea of so many options that we cannot use. Second thing is that this is a power inductor. When we want to deal with power, PQ and EQ cores are giving a really good performance. Then when it comes to the gap, we need to find a starting point. Normally 0.2, 0.25 mm could be a good starting point. And then here at the end, it depends on how many options you want to analyze. You could go 0.1 mm, let's say 0.25, 0.35, 0.45, and analyze many different gaps. Or like in this case, we wanted to understand with a step of 0.25 what happens, and therefore that's why we have there 0.5, 0.75. As you can see here, the combination of the EQ25 with 0.5 mm is the one giving us the first solution able to store more energy in the gap than that required by the inductor. If we go in the right side of the table, we can choose that. So we can select, for instance, EQ25 with 1 mm, but then we are just making our inductor worse, because this means that for having a bigger gap, we will need higher losses, and therefore we will have much higher losses in the winding. So in this table, we need to always look for the, let's say, the smallest gap that you can have for that particular shape. And in this case, the EQ25 is giving us the enough energy and the smallest component between the EQ25 and the PQ2617.
Yeah, I mean, if we check the, let's say, the volume, the effective volume of these three ones, PQ20 is the smaller one, then the second is the EQ25, and finally the PQ26. Then the smaller and the best option would be PQ20 with 0.25 millimeters, but the energy able to store is half the energy needed. Then we have to move in that direction, or in, well, first we have to go in low direction. Then if we come here, we see that EQ25 is not even able. Then now we move to the right, then again, I mean, the PQ20 is not able. Then the second option here is already able. I mean, EQ25 with 2.58, sorry. Okay. Now with this selection, we have to calculate the number of terms. No, I mean, there are no rocket science here. You just have to take this equation and get the number of terms. As you can see, we have choose, let's say, the lower value because since the losses in the core are very low, we can reduce one term, will means maybe a lot of savings in terms of winding losses, and the value of the gap probably will be very similar. Then which is 9 turns, and now there is an important and interesting thing that maybe at this value of components is not quite, let's say, critical or just maybe for the cost, but it's the decision of which kind of wire we will use. Then there are four options. We can go for a lead wire, rectangular, round, or foil. Then Lucas, can you give us a little bit of light? Which, I mean, what should we do? I mean, you are here, you have already your component. Why choose one or another?
Yeah. So again, we always need to think on how our waveform looks like, how the waveform is going to generate our losses. So in our case, we have a strong DC bias with very small AC ripple. This means that the most of our losses is going to come from DC loss. So this is one thing which tells us that we are not interested in lead wire, because there is no reason to go for a lead wire that is going to increase the cost of our component. And also, if we go for a lead wire, we will have lower conduction area for the same size of wire, so we will have much higher DC loss. And at the end, we have said the main source of losses is going to be the DC So release wire in this case makes no sense. Then we have to choose between round foil and rectangular wire. If we go for a foil winding, we will need to have isolation between each of the turns. Then this is gonna take some space. Actually, it's gonna make the manufacturing also more complex. And then we need to deal with the lead outs. We need to deal with how the foil is going to the PCB, which is gonna be also adding complexity to the manufacturing of our components. So in this case, the foil winding is not making any sense. And then we have to choose between two, rectangular wire or round wire. If we think on inductor with low amount of turns, we can go for rectangular wire because we can use the full window area in terms of width and height. If we have a lot of turns that we cannot put them in a single layer, then we will probably need to go for round wire. But in this case that we have few turns, we can go for a rectangular one.
Okay, then we will choose a rectangular wire, and there is no much more calculations that then just for the space we have to choose the width of the wire. Then because already the 9 turns will fix us the space, no, Lucas?
Yeah, the end here is kind of, let's say, we only need to take into account the manufacturability of the component. So this means we need to leave a certain space between each turn and a certain space between the winding and the core. If you do that, if you take into account the core height, then you take these spaces, which in this case was 0.25 mm between each of the turns, then you end up on a maximum height you can use and on a maximum width we can use. And if you take the full of that, then you are, let's say, maximizing the conduction area you have in your inductor and minimizing the losses in your inductor. And this is actually what we did here.
Yeah, definitely. Okay, and also we can see the losses. And now I move to a topic that I mean is very interesting to me. I mean, let me take out the laser. Okay. Okay. At some point, when you are using, when you are looking for an inductor for a specific application, especially in DC, I mean, these ones, I mean, we are talking about DC inductors. If you make the numbers, doing a customization, it could be one of the expensive things that you are going to do, because customizing a component is just not a customization of the design from a power electronics point of view. It's also a customization of a mechanical component and preparing a mechanical factory or a factory to build this mechanical component, building toolings and building a lot of components. And we are supposed to build more efficient power converters to save the world, reducing the CO2. And to be honest, the customization is one of the things that doesn't really help for that. We have to take energy from, we have to take material from one part of the world to the other. Also, we have to make a lot of iterations and tests, and finally characterization. And always I'm trying to find, well, which kind of components can be customized. There are a lot of, you can customize everything, but and which ones are not or is not recommended to customize is, well, those ones that manufacturers are providing good components that actually, if you check our final solution, is very similar. Very similar. It's a PQ or EQ 25, 0.5 millimeters of gap. Then if you come to this, for example, these data sets of burns, you can find components with, for example, in this case, for 22 microhenries and maximum RMS of 28 amperes and a saturation current of 14. Also, it's important to understand what means these application nodes. Here, what you can see, of course, that we always try to work giving more details in our simulations, but here you can make very fast calculations. First, inductance. You can filter by the inductance. 22 micro, okay, this is the inductance that I'm interested. Then checking the resonant frequency, here they give you a value. Take care that you are not working very close to that values. And then you have some values for DC resistance that allows you to make calculations about DC losses directly with the square of the current. Then the maximum, let's say DC current, RMS current, and the saturation. The saturation in this case, they also specify that when you reach 14 amps, the inductance will drop 20%. In our case, we were around 12 amperes, then that would be okay. And even in the worst case, if they go to 14, the inductance will drop 20%. It's not going to go down to 0. And even at 15, it's going to go that drops 30%. Then this is a component that even have AECQ 200 compliant. And I think that when you can use something from the catalog, go to that direction. This is my recommendation. I mean, don't lose the time doing just a custom component. Even if you spend a few hours checking or you need to find the component or some samples, it could be worth it at the end, not only for you, but also for the planet. Okay, next case and last is going to be design an inductor for a much power case where usually it's more difficult to find a component from the catalog. This is going to be a 12.5 kilowatt boost converter and 200 or almost 80 microhenries of inductance. Then here, what we are doing is exactly the same. And in the same case, in the first case, we extract the values that are needed for doing the calculations of energy. Then we have if the switching frequency is 18 kilohertz, the peak current 32, the volume in the variation of the AC is 9 amps, and the DC is 27. Also, we have to consider here the inductance as a value, and then we can go to make our calculations. But before moving that, I'm going to call Lucas again to say, hey, now there is any changes from before, which material should we use?
Yeah, now we have a much higher inductance. We are talking about 279 microhenries, and also a much higher current. So this means that the magnetic field we will have in this inductor is going to be, let's say, pretty high. So if in this case, it makes more sense to go for a powder core, because if we go for a ferrite, although it could work, it's going to be bigger, because we will need to give, it's going to be bigger or it's going to be more lossy, because we will need more turns to have a magnetic field below 300 millitesla. And therefore it's going to be bigger. It's going to be more losses in the whiteness. So in this case, powder makes more sense.
Yeah, I mean, I think that everyone working these levels, even if you check the pictures of these kind of inductors, you can realize that are based on toroids and commonly using powder material. In this case, actually, we will use the materials magnetics that we used to work a lot with those materials. But once you say, okay, you go to the page of magnetics, in the article of this week, I have described this method. And then you say, okay, now there are like, I don't know, 20 materials. Which one should I use? Lucas?
Yeah, so here again, we need to always think on the application. So in ferrites, we have application based on the frequency and the temperature profile or loss profile. Here is kind of the same. So we need to understand if we will have a very high DC bias or low AC ripple, if we will have an intermediate AC ripple, or if we will have big AC ripple. When we have a very, the first case, so we have, let's say, high DC bias, low AC ripple, we should go for a high flux or a material where the permeability drop is relatively low. This means materials like high flux will have a very stable inductance over the DC bias. Then if we have a lot of intermediate losses, we can go for a cool mu or sand dust, which will give us good performance in terms of core losses, intermediate performance in terms of permeability drop, but this is the cheapest one. So if you have also, let's say, to do trade-offs on core cost, the QLMU is one of the cheapest one. Then if you have, for instance, you are working with, in the first slide, you were showing a PFC in CCM mode or CRCM mode, where we have a significant ripple there, and therefore we have significant losses in the core. Then we have to go, for instance, for an MPP core that has the best in class core losses from these materials. But again, nothing is for free. You have better core losses. Let's say the core is more costly, and the magnetic field that this can withstand is much smaller. And then the X flux and the magnetic sets are somewhere in the middle between the MPP, high flux, and cool mu. So in this case, because of the current we have, we're in the boundary between high flux and cool mu. We could go for one or the other. If we go for high flux, we will have a better balance in the losses between core and winding. If we go for cool mu, we will have a bigger permeability drop. We will need to go for higher turns, higher number of turns, and therefore we will have more losses in the windings. So in this case, to have a better balance between core and winding, we are going for high flux.
Okay, I think that this is not a very simple decision. Then that could be one part that maybe at the end of our presentation, people can make questions and we can discuss. Of course, that we are not field application engineers of magnetics, then probably we won't be able to answer with the accuracy of them, but as some users, we have some experience with some particular materials that maybe is very useful. Okay, if you go to the magnetic page and my article, you will find that I'm following a method that they propose, and the method is basically that you have to find your core. Actually, once you find the material, then you have to go first. I think that I put the slide in the reverse way. Yeah. No, I mean, but I have to choose the magnetic component. Then with the energy calculated, then you have to look for the component with the high flux. In this case, because we have choose high flux, you have to go to find which high flux toroid have greater energy than you have minimum or you have calculated. Then in our case, it was this core. And then once you have the core, then with this equation and the datasheet that is in the same PDF of the process, you can calculate the number of terms. The problem with this kind of material is that the permeability drops with the current, and then you have to make some calculations to have the final value of the number of turns to ensure that you will have the inductance that you require in a specific current. Usually this inductance is, like, say, for almost zero current or maximum current. And for doing that, then you have to go to the permeability versus DC bias and then find the component material that you are working with. In this case, is high flux toroids with material of 60 microhenries of permeability. And you realize that, well, finding the value, this case is 90%, and with this, well, 93%. And then with this value, you have to calculate the new number of terms. In this case, is moving to 40 terms. Now we have to take again the decision. I'm going to move forward here because we are running out of time, and I want to have time for doing some fast calculations of Lucas. The method of magnetics, they propose to use most of the cases round. Then is round the selected one, and it's very simple. You just calculate the component with the rule of thumb of the current density you want to have. For having something, let's say, not in a risky position, choosing 5 amperes is a good decision for this kind of components where there is no, let's say, high losses because of proximity. Well, there are losses of proximity, but there are no different layers. Then the losses, the AC losses can be under control, more or less, if you put only 1 layer or 2 layers maximum. And then you have to move to, well, this is the area you need. And there are several ways of having that area. One is to get, let's say, a big wire, and the other one is to use several in parallel. But, well, Lucas, if you want to comment here, why, I mean,
yeah,
choose, or we have chosen the number 12.
Yeah, at the end here, if you do the math, you end up on a big wire. The width is 2.5 mm. Then working with this wire is kind of, let's say, tough or complicated sometimes. Not maybe so easy to deal with in manufacturing. I mean, in the factory. So therefore, sometimes makes more sense to go for 2 smaller wires, which is what we have done in this case. Also, in this story that we have low, let's say, filling factor. So if we go for a single wire, we have even lower filling factor. But if we go for 2 parallel wires, we can increase the conduction area and reduce the losses of our component.
Okay. Well, doing just the calculations of most of the losses are, these losses in this case are 16 watts, and if we include also the losses of the core, we will be having around 32 watts of losses, which is well, fairly good for this case. Now we will move to do some calculation with Frenetic. As I said at the beginning, it's just not kind of demonstration, it's kind of doing the calculation to see the differences when you are comparing different components with different magnetic fields and trying to understand why choosing some options and which and not others. And also finding that when you are doing the calculations manually, also you have to choose which core shapes or material you want to use. Then with Frenetic, we have capability to do more analysis, then we will see more options and then finding why in some cases is even just good to use these high flux and which not, which cases is not. Then Lucas, if you want to share your screen, once we finish this part, it's going to be short, then we will start the Q&A session. We are a little bit, maybe we will end 10 minutes later, as predicted at the beginning, but I think that we are on time.
Chema, please, if you make me hoster, then I can...
Okay, let load me.
Yeah, now it works. Okay. So I'm gonna show you, do you see my screen, right?
Yes.
Okay, so I'm gonna show you this first. Let's go step by step. I'm gonna show you the back inductor, and then we're going for the boost inductor. So we are going to fill in the specs. The inductance was 22 micro, the switching frequency is 100 kilohertz. The input voltage was 48 volts, the output voltage 12 volts, output current 10 amps, and therefore output power 120 watts. Now here, what we can do is, as I said, or as we said at the beginning, is define what is the maximum field that we want to have in our component and check what is going to be, let's say, the core loss and the gap for that particular core. So I'm going to define 300 millitesla, and I'm going to choose a PQ family, and as we decide at the beginning, 3C92 material. So now what we will see here is the effective volume of the core versus number of turns. So this means that if I go for a PQ 2014, I need to have 16 turns to have a magnetic field below 300 millitesla. This is going to be the power density of my inductor, which has this dimension in width, depth, and height. And here we can see what is the inductance that I get and how much gap do I need in the center leg. So I need one gap of 1.18 millimeters. By here, we can check different cores. So before we were talking about the EQ and we were talking about the PQ. So if I go back here, what I can see is that for the PQ 16, 17, because it's bigger, I need less turns. That's for the EQ 25, where I needed 9 turns. Now we can extend this analysis to any shape or any material, but well, since we are running out of time, I'm gonna, let's say, keep it here and show you our second graph, which is also very useful, which is, okay, now that we have seen, let's say we have selected these 3 cores, let's compare them in terms of performance. So if I select the PQ26 again, 3C92, and I plot it, what I get here is the evolution of the losses, and losses, gap, and magnetic field for this core. So for instance, with turns, I have 0.75 millimeters of gap, but if I go for very large turns, then I start to have a huge gap, which I do not want. And as I said, we can compare with the PQ 2020 that we were discussing at the beginning, and we can also compare it with the EQ core that we were discussing at the beginning. Now, what we can see here is, let's take a fixed point, okay? For the EQ 25, I was saying that I wanted to have 9 turns, and this means magnetic field of 300 millitesla, 0.11 watts. If I go for the same in the PQ 2020, what I need is around 14 turns. So this means I will have much higher winding losses because I have more turns, and because it's smaller, I have less space. If I go for the PQ 26, it's the other way around. For having close to 300 millitesla, I can have lower turns and therefore lower losses. Yeah, but let's continue with the EQ 25. So I'm going to apply, and then here I'm going to get what is the magnetic field, AC, the magnetic field, the peak magnetic field, and also the saturating current of my inductor. Once we are happy here, we can also define the winding. So we can, as we said before, we can define a rectangular winding, which is going to be one parallel, a winding of point. Let me see. I cannot see this because of the. Let me see if I can move. I see here the zoom window. Yeah. So I can select a 0.7, the width of 3.9, and now I can check my total loss, which is pretty small for this 120 watt power converter. Yeah, there we go. So we have 0.39 watts in the inductor and 0.08 in the core and 0.31 in the winding. So this is the sample for the low power one. Now let's go, let's do the high power one. So I'm going to do the 12.5 kilowatt boost inductor.
In any case, I think that something interesting is that for the low, well, the smaller inductors, well, you can analyze a lot of options that at the end, the main limitation is the height or the dimensions, and then you just need to filter. And if you have a great database of components, you can have a lot of options. And this is good, especially nowadays that we are, let's say, out of stock in a lot of cases. And in this case, for the high, let's say, high current inductor, it's very similar at the end. You need just to ensure that what you are looking for is also in stock. And I think that this is quite important for doing the calculations very fast and ensuring that you are not losing your time. I'm going to start also just with some questions. In the meantime, I already have answered one that was asking about if the magnetic field was in millitesla, and it was yes. And so Tiris asked if the calculation of for the energy, if we have to ignore the DC bias.
No, we do not.
No, because it's I mean, basically you are using the instantaneous current for the energy. Then you have to take the real, I mean, the real peak. Same thing if you are in a DC, in a AC case, like in this case, is the real peak, because it's the instantaneous energy.
Yeah.
Okay.
Yeah, I realized I was putting 100 kilohertz, but the sign we did was 80 kilohertz. And also in this case, actually, I think you mentioned this in your paper. This is from an application note. I mean, we took this specification from an application note from P, and there they have some cooling, so I have just include here the forced convection, so we can consider that. Yeah, and I don't know if you saw it, but basically I have selected the core from magnetics with this high flux. And what we got is kind of the same result. We got these 40 turns, and in the winding losses, I use that round wire with 2 parallels, and we get 17 watts of losses. Interesting thing here also is that we can check what is the evolution of the inductance with the DC current. So if we put here, for instance, from 0 amps to 150 amps, what we can see is how the inductance drops with the current. This simulation normally takes a few seconds. So Chema, if you want to also answer some questions.
Yeah, I mean, let's start with questions. I mean, the first one was like, hello, I'm new on the inductors design field. Could you please search an example of a core parameters table? Can this be found from a standard supplier website? Yes, I mean, actually, Lucas, can you show, let's say, data set of component, for example, the previous one? I mean, if you go to ferrosteel or magnetics and so how to find the data set. No, but use Google or something just to allow the people to use to find by their own.
Give me 1 second. Just
well, the key is that yes, I mean the answer is yes. The key point is that not all the manufacturers provide, let's say, easily the materials in a good way for everyone in internet, but there are some of them that yes. Well, here for example, if you write the EQ25 ferrous cube, you will go directly to the data set, and here you will find the dimensions. Well, explain you, Lucas.
Yeah, I mean, basically always you have the dimensions of the core with the minimum and maximum tolerances, and also you have the materials that they have typically available with these cores, and then the inductance tolerance for each of the cores. And also one thing new that nowadays some of the manufacturers are including, which is what is the magnetic field peak maximum that they recommend for that material and that core shape. This was not, let's say, this is something new from manufacturers, at least from ferrous cubes. In the past, this was not there, and you get only the magnetic field of a certain material, but not of that material with that particular shape.
And for the magnetics, well, and also the catalog of ferrous cube, there is a catalog for all the cores, and you can find everything.
Yeah.
And magnetics is the same. There is in the link of the article, you can find everything. Okay, thank you, Luis, for the question. There is someone anonymous that say, for choosing the ferrite core based on power of the transformer, it is important to consider input and output power simultaneously, or just one of them is enough. I mean, the chosen core must be capable of handle the sum of the input and output power. Well, today we are talking about inductors, but here, I mean, just analyzing when you are choosing the ferrite core, you are choosing the range of the power level. Sometimes, for example, for the area product method, then is the output power, and assuming that the output power and the input power is going to differ, just the efficiency, then just one is not that you have to choose two. When is foil wire preferred? Lucas, this is for you.
Foil winding, normally we recommend it for transformers when we have a single turn in the secondary side, when we have a big ratio from primary to secondary side, we have a single turn in the secondary side, then we can use foil. But there is one thing important with the foil, that you need to be careful with the lead out, how these terminals are going to your system. And it's also interesting for very, 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 very large power inductors, like for instance in inverters, I mean AC grid inductors, these 100 kVA, 500 kVA electrical steel big inductors, where you need to have a huge amount of cross section. Then what you do is you use a single turn like this size, then you take several foils in parallel. These are, I would say, the most useful applications for foil.
Okay. Well, Florin asks, how do you calculate proximity losses? When in this case is manually in the process that we have published, actually we don't calculate proximity losses manually, because we are not considering that losses in this process. We do a Frenetic, but as I said at the beginning, we are not going to enter in that part. Just say that, for example, if you follow the process of magnetics, there are some comments about some losses you can consider, not proximity losses, just some other losses in the core and basic losses in the winding. And for the ferrite one, if you have only one layer, well, I mean, also you can consider probably are going to be relatively low, but of course that you can use models for doing that calculations. Do you want to comment some models, Lucas, about proximity losses? Or...
We use Salva. I don't know if people in the
audience use Frenetic, but not manually. I mean,
yes.
I haven't used that one manually ever.
Yeah, if you want to do it manually, then you need to be, let's say, you need to have a lot of time. If you want to do it manually, so we always recommend to use software for that.
In any case, for these DC cases of one layer, maximum two layers, actually, if you do two layers, probably even it's better to use double, just with two layers, and get the relation, and that's all. How to choose the lead wire? Well, I think that here the main thing to choose a lead wire is to talk with, well, having the lead wire, because most of the manufacturers for production, they build their own lead wire or they customize the lead wire. Then of course that Grua Due or Electrisola, they have catalogs of of lead wire, but the reality is that if you ask them, they are going to manufacture it that day. Then it's better that you make the calculations or you verify which lead wire there is there in the market. As thinner and complex you build is going to be much more expensive, and maybe it's not going to solve you anything about losses, especially in a DC inductor. But as a rule of thumb, probably you have to choose the diameter of the small string due to the skin effect, not, I mean, with crazy smaller values. Actually, the recommendation, Lucas, is zero. I mean,
I would never
kilohertz.
go, yeah, 100 kilohertz, you can go to 0.1, 0.07 if you have a lot of harmonics, but I would never go above 0.05, 0.04 if you are not in the megahertz range.
And in number of strands, this is also critical. I remember at the beginning of our designs, we built up, I don't know, 2,000-3,000 strands case, and that was impossible to manufacture. Then always you have to think that at the end, the mechanical, it should be something easy. I mean, easy to manage the thickness of the diameter. Okay, only 4 or 5 more. What would be the typical value of current density for wire selection in case of transformer design? Is there any trade-off for its selection in case of inductor and transformer designs? Again, this is the rules. The rules of 5 amps or 10 amps is more for inductors, where there is no big implication of AC losses. Once the AC losses start to play in the game, the current density becomes crazy. I mean, it's totally different because, for example, in a planar transformer, you can have 30 or 40 amperes per square millimeter, while in these cases we have 5. But the reason is that the AC losses decrease a lot. Then for the transformer, I wouldn't say any value because I would make a mistake for sure. I mean, the range is huge. Then for transformers, it's going to be case by case. Or if you are doing a very, let's say, simple transformer with just 2 layers, where basically is the minimum layers you can have, then never go to, I don't know, if a concentric transformer, 8 amperes for DC, for the DC, assuming that you will have relatively low AC DC ratio. What do you want to say something? Or
no, I mean, normally it depends.
Maybe
it's very tricky because at the end you can, it depends on the frequency range. You can go, for instance, if you go for very, very high frequency, then you need to take care of minimizing the number of layers so you don't have proximity there, rather than putting more parallels. For instance, if you go for very high frequency, you can just want to reduce the current density, and then this means you put another layer of wire in parallel, and then this is making things worse, not better. So it's not a straightforward answer because it depends on the case. You can always stay on the 5 to 10 ampere per square millimeter, but it's not a fixed rule. You need to understand how your waveforms look like and how they are going to affect the losses in your magnetic.
All the losses, I mean, all the questions refer to the simulator. I will send a private answer because it's not the focus of this seminar. What is the difference in the core material of an inductor and a couple inductor? I don't have any idea. There is no differences.
I mean, it's the same.
I mean, there is differences in the selection because the area product doesn't work like this, because basically you have it's kind of two windings, but the selection is not different. I mean, the method is different, but
talking about couple inductors like power couple inductors, if we consider a common mode choke a couple inductor that we can consider it, then it's a non-crystalline core which has nothing to do. But talking about couple inductor like back versus multi-phase back, then the ferrite is just the same material. There is no difference there.
okay, there is another question. When we take core of inductor required lamination, basically when you are at very, very low frequency, like 50 Hertz, then you use vertical steel, I mean, in lamination, or for very huge ferrite cores, then you have also to split in several acts to avoid losses.
Yeah. Eddy currents in the core at the end.
Eddy currents, sorry.
Yeah.
How do you determine how we are determining temperature rise? Yeah, this is a great question. My recommendation is to take an analysis of the thermal resistance of the component and doing the calculations with, I mean, multiplying the losses by the thermal resistance. Typically, the people use software for doing these calculations, but the models need to be very well. I mean, we have been working in these 3 years, and now we are happy with our results. But it took us 3 years to really understand what happened there. What I will say is, based on your experience, I mean, take notes of evolution of temperature of a specific component, then calculate the thermal resistance, and then extrapolate. Is there a rule of thumb to know when it's necessary to use lead wire?
When you have, I mean, you need, again, I'm very insistent on this, you need to know how your waveform look like. So in this case, we have a percentage, I mean, the ripple was kind of 15% out of the complete current. So I would say if you are having somewhere in the range of 25 to 40% and above, so this means 100% is pure AC. If you are from 40% to above till 100%, then this means you have a significant AC component in your waveform, and therefore you can go for a lead wire, or at least try to analyze it.
Okay. How will mechanically secure inductor having air gap? Do we use glue between core air gaps, or only tapes to grab over the core to hold tight?
No, you need to glue them. I mean, it's not possible. When you go for distributed gaps, I don't know if that was the question. I mean, if you go for distributed gaps,
no, just for what I think that the question is, what do you do?
You have
just with the gap. I mean, glue or putting the clips, or
you can do either gluing, you can do either taping.
But the best, no, but I think that the question is, you have to ask the manufacturer to give you the core already with the gap. Then you don't have to put anything in the 3 legs. Then this is the most professional way.
Yeah.
I mean, ask the manufacturer or buy a core that already have the core. I mean, the gap is gapped. If not, then if not, you can use different solutions. But at the end, since you will have, glue. I don't know, glue.
Yeah, I mean, I would recommend to glue it, varnish it, so everything is gonna be, let's say, properly secured and not moving there, because if it's not varnished, then it could be moving. You glue it, then you varnish it, then I would say it's the best way.
In the area product method, how to select the delta B? This was one of the reasons I wanted to share Frenetic to show the delta B's, because the delta B is something you calculate with the waveforms, and then with that you can calculate the area product. But this is something that depends on the waveforms. I mean, if you check in the article, the picture, actually the second picture, there is a graph where you can see the variation of the magnetic field due to the waveform. And this is the delta V. You can see there the delta V. Then go to the article and you will find it. Does planar profiles are considering for inductors? If yes, winding copper losses cladded PCB board are we considering? How is making advantage than other wires, as you mentioned in today's slide?
PCB versus
why
PCB.
not?
That's the question.
No, the topic is if planar profiles are good for inductors or are considered, and yes, I mean, why not?
I mean, I think there is always here one thing, which is we have to talk about, in my opinion, planar technology as PCB technology, because the core, we don't care whether it is planar or not, is a core. We can put an edge wound winding as we did in this design, and you can use a planar core. I mean, but when we talk about planar transformers or planar inductors, we need to talk about inductors with PCB windings, not the core. The core is not defining for me the planar technology.
Okay.
Guys, I think we have run out of time already. We are 20 minutes over the scheduled time.
Let's solve the last question,
okay,
and then we can close. How eddy current on winding wire, particularly at air gap area, which impact on winding losses?
You will have a big impact because at the end you have a fringing field there, which means that it will increase the losses of your winding significantly, of course. Yeah.
Okay, and well, there is a guy that said that had good insight about the inductor design, request you to organize a seminar about high frequency transformer design as well. Yeah, we will do, definitely. Yeah, well, thank you very much, everyone. We have been, thank you. I mean, almost 60% of the audience have been keeping until half an hour later. Then I'm sorry for those that we haven't been able to answer all the questions, but we are always open to receive your questions by email. You can write us directly to Frenetic or through LinkedIn or whatever you want to write us. We always try to answer questions. Okay, well, thank you, everyone. Thank you, Lucas. Martina, if you want to close.
Of course, we want to thank you again, and the recording of this webinar will be available on our YouTube channel in the next days. We will send you all to all the participants the link with the YouTube recording. And of course, if you have any question that we couldn't answer today because of the time, please contact us. And of course, we will try to answer you all. Again, thank you, and see you in the next episode of the webinar series. Ciao.
Thank you. Bye.